He's already on my left-hand side. Keith Clark has first degrees in both mathematics and philosophy and a PhD in computational logic. He's an emeritus professor at the Imperial College London, an honorary professor at UK Brisbane and UNSW Sydney. He has taught courses at Stanford, Syracuse and the UC Santa Cruz in the US, at 3 universities in Sweden, 2 in Africa and at the University of Queensland. He is here about probably the longest presentation title. He is here to talk about rule control of TeleoR reactive, multi-threaded communication robotic agents. Ladies and gentlemen, Mr. Keith Clark.
Okay, thank you. Well, I've decided I'm going to give this talk backwards, in the sense I'm going to give you what I would normally demonstrate towards the end of the talk at the beginning. Now, a colleague of mine, he's in computational logic, and the main inference system that we use is the one for ProLog. And I don't know if you know, but it's backwards reasoning, right? It goes from the goal to the preconditions. Well, a good joke that was once told about him by another friend of mine was that whenever this guy tells a joke, he gives you the punchline first. So I'm in a way giving you the punchline first. Okay, so basically this is about programming languages that considerably facilitate, when you gain the skill in using them, programming sort of intelligent and, you know, in this case, multitasking and communicating, right? So we do the lot. So that the robots can, or the robot agents specifically, can multitask, control several robotic devices, you know, and interact with them, and I'll show you that, and also communicate. Okay, so this would be the final thing I was going to show you, and it's a program to control a Baxter robot. Very simple, of course. It's just doing tower building. And the task, there are 2 concurrent tasks going on, okay? One is to construct the tower LAB here, and the tower COT there, okay? Now, you can see that the C is on the wrong side, okay? And these are like little tables, and the blocks can only be placed on these patches of cardboard, okay? So, these tasks are going to dynamically use the arms. There isn't a fixed allocation of which arm should use which, could do which task. So if this C was over here and the L was over there, then only this arm would be needed to construct COT, and only that arm lab, right? But we have to move blocks away, right? And the reason why we've got this middle pad is because C has to be moved by the right arm to the middle pad, and then the left arm is going to move that over, right? And we don't want the arms to clash. So there's lots of problems in this thing, right? And I'm just going to start it's a video. And I'm going to have, there's a human here that's helping and interfering. Okay, so the first thing is the lab task is kicked in, right? And it's going to move the L over there for the right arm to pick it up, okay? Now the COT task is kicked in, right? Because remember, we're doing concurrent tasks here, and it's moving the C to this middle area, okay? Now, as an optimization, it could pick up the L as it's going, but it doesn't. It swings across. Now, I've got help. Now we can use parallel use of the arms, because they're not going to interfere with one another, right? So now we can do this, the 2 tasks. We can finish the 2 tasks concurrently. Okay, now interference, right? So these programs are achieve and maintain, right? So if you like, the computation is constantly monitoring. So we're back to the initial situation now. Okay, so it's picking up L. Now another help, and so we got concurrency. Okay, so it's how do we handle that with a very simple program? Well, underneath the engine, as it were, is quite a lot of complexity in the implementation that makes the programming of this quite simple. I'm just going to, at the end, I'll give you a little glimpse of that program. Okay, so, oh, sorry, I'm going to give you some more demos as well first. Where's my specs? Okay, so this is a communicating problem, and again, it's very simple. It's just 2 robots collecting bottles, right? I'm just going to show you one here, right? So, right, and I can tease it by moving stuff around. Okay, thank you.
This is not safe.
Right, okay. Now I'm going to start the other one. Sorry, I should have done this ahead of time. Okay, now they're both going, and that means, okay, thank you, that they might collide, okay? So I'm going to try and make them possibly collide. Where am I? I've lost my mouse. Where has it gone? Oh, there we are. Okay, well, in that case, one woman, they touch one another. Well, I want to try and make them, and they've also got a joint task to collect so many bottles. So when they've collected so many bottles, so what they're doing, each time one delivers a bottle, it communicates to the other one. Right, let me do another. Okay, now they've avoided one another, right? One stopped, getting out of the way, and the other one's picking it up, okay? So we want to be able to do that. We want them to talk to one another. Oh, and the constraint on this is that each robot can see the other one, or each agent controlling a robot, specifically, that's the software, can see the other one, but doesn't know which direction it's going in, right? And so what happens in the program, they say, okay, I can see you on my right, I can see you on my left, and they use that information to avoid one another. Okay, another demo, okay. Oh, this should be slower. It's, oh, well, never mind. Okay, the tower building thing now. This also, can't do it. Don't know why it's not moving. I want to deconstruct the tower, but I can't do it. I don't know why. Oh, well, I'll have to come back to that later. Okay, so what I want to do is to show you what I can do with this program. From the same program that will build one tower, I can very easily make it into a multitasking program that can build 3 towers, very easily. I'll show how to do that. And then finally, that Baxter one is just an elaboration of that program, where instead of being one arm building it, there are 2. And of course, we've got help and interference. Well, we can do help and interference in this one. Okay, back to the main story. Okay, so I'm not going to go into details here, but basically there are 2 programming languages. TeleoR, which is the one that's a rule-based language. They're both rule-based. That's going to be controlling the robotic side of things. Okay, and this thing goes way back. I don't know, how many people remember Shakey? Shakey? Good. I mean, we're really going back a long way. We're going over 50 years. Okay, Shakey was a robot that was built at SRI in the States, in California, which at that time was Stanford Research Institute. It's not anymore. As the first cognitive thinking robot. And it used to plan, shuffle around, and it basically moved boxes together, colored boxes. Right? It was actually a seminal piece of work. Okay. Well, this language, TeleoR, is a descendant of the way they represented plans in that Shakey robot. Okay? It's a descendant via various bits of proposals that Nils Nilsson was the head of the group that built that Shakey robot. And through various papers, he proposed, it eventually evolved into this programming language. He called it TR for tele-reactive. And then we further extended that. We've made it a much more robust programming language. Unfortunately, Nilsson died a few months ago. It was a real tragedy. He was one of the giants of artificial intelligence and cognitive robotics. Okay, so this itself, and I'm not going to go into details, is built on, a logic programming language which is typed. Now, why do we want types? Okay, normally, if you're familiar with Prolog, it's untyped. But we're going to be eventually sending out things, possibly via ROS, to a real robot. And we want to make sure that when we send those things out, they're correctly typed. Okay? So that means that in the thinking language, in the inference language, we have to have types. Well, we could do runtime type checks, but it's better to validate the program at compile time and know that there's going to be no type clash between the primitive actions you're going to send out to a robot and the reasoning component. Also, if you're familiar with Prolog, Prolog just uses the same syntax for imperative things like reading and writing and sending messages as it does for thinking things. And that's not nice, it's not clean. And modern functional programming languages separate them. You have a pure rule-based language, as in Haskell, and then you have these sort of things like monads for things that change the world and do input-output. Well, we did the same with this QuLog language. So we divide it into a declarative subset and an imperative subset. Doesn't matter, but in the declarative subset, and we also then integrated functional logic programming. So it's actually a very powerful, very expressive knowledge representational language. And you'll see a glimpse of it. Okay, so this is I'll show you the program, the essence of the program for that bottle collecting. It's a very simple one to explain. Okay. All right, so forget this. This is the housekeeping. All right, this is the type housekeeping at the front. Thing, is a bottle and thing. I'll say what directions are. Okay, so this thing is important from point of view of what messages are sent out to either a simulation, as we were doing there, or a real robot. And we've run this, we've used this program to control a Mindstorms robot, for example. And then, of course, that gets sent out using Wi-Fi. Okay, so this is the main top-level procedure, which is to do collecting. Now, as a plan, it's back to front, okay? In the sense it always starts with, have I finished? So the precondition of the first rule is always the goal of that task. And if you like, invoking collect bottle that's the top level procedure of the task procedures. Okay? And have delivered has got this sort of very simple Prolog style definition, which says, okay, if the robot can see the drop at 0 distance, it can infer that it's next to a bottle, and it's got a sensor, percept that says the grip is open, we'll count that as have delivered. Right? So if I started this program out with the robot right next to the drop, the drop is, okay, let's, see this is the drop area. If it started right next to the drop and in front of it was a bottle, it would just stay there. It's like a dog with a ball, right? If you start off the dog and the ball's at your feet, then it'll just sit there until you throw it away, okay? Or in this case, until the bottle disappears. Okay, so you start with the last thing, right? And then you have, as you go down these rules, you go to sub-goals of that last goal. Now, in this case, it's a linear sequence of sub-goals, but we'll see later it can be a tree of sub-goals, okay? So this says, well, if I haven't delivered yet, what's maybe wrong? Well, it could be that I'm seeing the drop at 0 distance, but I can sense I'm holding something, right? Right, in other words, I won't get the perception that the gripper is open. So what I should then do is open the gripper, and that's a primitive action. It's a primitive discrete action. What's the difference between discrete and durative? Well, durative is an action that once you start it, it will continue unless you explicitly change it or stop it. Right? Discrete action is something that will stop of its own accord after a finite amount of time, and it's not interruptible. Okay, those two types of action. Right, so suppose that's not the case. It cannot infer from the sensor data that it's got, which get converted into these percept facts, that it can see the drop at 0 distance and holding. Suppose it can infer, and it's got the sense data, that says it's holding something, right? So we imagine there's little sensors on the grippers. Right, then in that case, what it's got to do is to get to the drop. And if it gets to the drop successfully, it should see the drop at 0 distance, and if we're lucky, it's still holding it, okay? Now, finally, there's this catch-all. well, suppose none of these hold, as nothing's helping me, then what I should do is get hold of a bottle, okay? And these are defined below. Right. Suppose that whilst it was doing get to drop, okay, it dropped the bottle, all right? They fell out of the grippers. Oh, how am I doing? How am I doing?
A little over 10 minutes.
Okay, then I must move quickly. Then what would happen is it would drop down and do this rule, okay? Because every time it gets new sense data, it checks the last rules that have been used, right? It rechecks them. It's almost as though it's a new situation. And it says, I'm no longer holding it, therefore I'll have to drop down to doing the last rule, okay? So these things automatically recover. And we saw that when the human was helping and hindering the robot building the two towers. It just said, okay, there's a new situation, let me start again, all right? Moreover, if you already started it, holding it or something like that, then it wouldn't bother doing get to drop, all right? Because when this sequence of rules are evaluated, always this thing is test. So the programs, if you like, are optimistic, and they all automatically recover, all right? So if you help it, it will jump up the rules, and if you hinder it, it will drop down. Okay. That's just filling in. They're very much the same. They always start with a condition that is the goal of getting bottle, and then they have sub-goals of that as you go down the sequence. Okay, now one thing that is a tricky thing in robotics, in cognitive robotics, or people worry about, is the interface between the reasoning component and the reactive component. Well, with this sort of language, it's just procedure calls, okay? So you have an initial procedure which has preconditions of rules that make use of defined relations. In other words, they're a higher level view of the sensor readings, the percepts you've got in, right? And then they invoke an intermediary one that does a little bit of reasoning, that's the I1 and the I2. And then finally, they invoke things right at the bottom that just directly read the percepts, okay? So you're going from reasoning to reacting through a sequence of procedure calls, right? And always, it's constantly rechecking the thinking bit, right? So as it gets a new set of perceptions, it says, am I correctly invoking Q and invoking R? And if I'm not, if another one of those rules is the first rule to be fireable, or the one that was used last time no longer has its precondition, it will do something else, right? So if you like, you're always thinking, am I doing the right thing at the top level, right? You're always doing that, and you'll change your mind about the low-level stuff automatically. As well as, if you're doing the correct thing, you react. You react directly to the percepts, like you follow corridors and stuff like that. So that's a nice feature of the language. Okay, so this is the two-threaded architecture of communicating. I like threads, okay? I come from concurrency. And so what happens is there's a thread inside the agent that is interfacing to the sensors, possibly to ROS, and it's constantly updating the percept facts. And on top of the percept facts, you have rules, and that's called a deductive belief tower. Okay. And then on the other side, you have this action tower, which has got a hierarchy, as we've seen, of telereactive rules. And those things are always atomic. So as soon as, when the fresh percepts come, there's an atomic update of the percept facts. And then as soon as the percept facts are updated, this evaluator kicks in and atomically reasons to find out the appropriate action for that latest set of percepts. It then performs the action by sending out instructions, goes to sleep until the next lot of percepts come in. Okay? Now, if you've got a communicating robot, it gets a little bit more complicated in the sense you have a message handler there. So not only does the belief store get updated by perceptions, it also gets updated by communication. And we make use of this, we have a communication server that is both a publish-subscribe server and an address message server. So you can address other controlling agents using something like an email address, ag at host, or you can just publish information. And if other agents have done a subscription that actually covers that published bit of information represented as a logic fact, then it will automatically go to that agent. Okay, it's a standard sort of thing. And that itself is very powerful, that combination of published and subscribed and address messaging. Right, now, another nice thing about doing multi-threading, and I haven't got an example of this, is you just throw in extra threads, okay? So, for example, suppose we've got this task thread going, and another agent sends a query to this agent, which requires some inference, right? Well then, in order to protect the message handler, you don't want to do the query solving inside the message handler, because there might be an error in the query solving, or it might run forever or something. So what we do is we fork an extra temporary query thread, and then the message handler thread monitors that, and after a certain amount of time, it will kill it. Because you don't want to use up a resource. You don't know what that query is going to do, right? And you might say, okay, I'll give it a few milliseconds of computation power, and after that, I'll just kill it, as I won't answer the query. Okay, there's another thing we can have. We can have a SLAM thread that's monitoring the actions, if we record the actions in the belief store, right? And looking at the perceptions of the environment and building up a map of the environment, right? That can be going on concurrently. Now, how can the task thread make use of it? Well, it's very easy. You've just got to get a common ontology, and whatever facts are going to be put in the belief store via the SLAM thread, the task thread knows what those predicates are, knows what those relations are and those facts, and you just program those as rules. And it doesn't matter if that information isn't there. The rules are just skipped, right? But as soon as that information gets put in the belief store by that SLAM thread, these rules kick in. You have them before the default rules, and they just automatically kick in. So as the thing is learning about its environment, it will automatically improve its behavior. Similarly, you can have something like I don't want to go into details. There's some technology in logic programming called constraint handling, and have a constraint handling rule, and you can do that for like obducing. You can resolve inconsistencies of beliefs. So this thread can be monitoring all the time. For instance, there might be inconsistencies between what the agent's been told and what it's perceived, right? And this thread can be resolving that in the background, right? And the nice thing about this approach is it doesn't matter if temporarily you're inconsistent, right? Because all that will happen is you'll do a dumb thing rather than a clever thing. But as soon as that inconsistency is resolved, the agent will start doing cleverer things and the correct things and send the appropriate actions to the robot. Okay, well, I don't want to go into too much detail. This is how we make it cooperative. And this thing, you see, this thing at the beginning, there's something it's got to react to. Every time one of the controlling agents sees or has a perception, or it can reason from its perceptions that another robot is near, we want it to do the avoid behavior, right? And so that's not part of normally the rules, the standard rules here, have this sub-goal structure. And this is the sub-goal thing. This is the achieving. What is this cooperative bottles collector got to do? It's got to achieve that its count of bottles plus the count of the other agent's number of bottles collected is greater or equal to some given total. That's the goal of the cooperation, right? And then there are sub-goals of that, right? And this is just little behavior. This is forget this. This is getting away from the drop to get out of the way of the other robot. And then these are the ones we had before, okay? But there's a reaction. It's like an emergency. It's almost like error handling, right? Where there's an unexpected situation. You don't have a sub-goal of trying to get near to the robot. Quite the opposite. You don't want to get near to the robot. So it isn't that in the sub-goal structure of the normal rules, you just want to react to it. And so we have this separate layer at the beginning of these emergency reaction rules. Okay, so this is a little bit fragment of the tower builder, which is similar to, well, it's essentially the core ingredient of that Baxter thing. This is a definition of sub-towers, of towers. Okay, so this is the very, very little bit of belief store knowledge to do this thing. And again, the durative actions, pick up, block, and so on. And this is make tower. Let's actually just look at this, because it's got the same sort of structure. But now, instead of being linear, so should I stop? 2 minutes. Okay, that's all I need. So instead of being linear now, it is a tree, okay? So again, what's the goal of building a tower when you give a list of blocks? Well, you can infer from the perceptions, and the perceptions just tell you which block is immediately on top of which other block, that list of blocks you've been asked to configure of a tower is indeed a tower, okay? That's a little inference you do using those tower definitions, okay? Now, here are two sub-goals of it. Here's a sub-goal. Well, suppose there is a tower there, but there are extra blocks on top. Well, in that case, the thing the sequence of blocks you've got is a sub-tower of a bigger tower. In that case, you make clear the block that's the head of those blocks. The other sub-goal, right, and that will achieve that. The other sub-goal is that, well, you've got a tower of the rest of the list of the blocks, not the full list, right? So if the full list had 4 block labels in, you've got the tower of the last 3, right? So you've got a tower of the tail of blocks. Well, in that case, you've got to move the head of blocks, which is the last block, from wherever it is to be head of the tail of blocks, right? And that could be, the head of this block could be buried in another sub-tower. But wherever it is, you've got to move it, okay? Finally, these are like, if you like, the base. This is the base case. Suppose you want to build a tower of 1 block. You've just got to move that block from wherever it is, buried inside another tower possibly, to the table. And then here's the recursion. Suppose nothing helps you, then what you do is you forget the lead block and you make a tower of the remaining sequence of blocks. What that will do is achieve this, and then with another action, you'll achieve that. Okay, so you've got a tree structure. And that's how you write these programs. You think in terms of sub-goals. And someone else, I was in a talk about task-level programming. Well, this is similar to task-level programming, except it's goal-level programming. Okay, I'll stop there. And that's the multitasking architecture. Let's not worry about that. It's a bit of spaghetti. That's what's going on underneath the engine. That's the thing I've already shown you. And here are some sources, if you're interested. And what we want is users of this language. We've already got users people in Brisbane are using it, in University of New South Wales, and a university in Italy. Okay, thank you.
Thank you. Keith Clark.